Hi, my name is Brent, and I have an exciting presentation prepared for you today. For example, I'm going to make quick cuts to try to keep things moving, and my cats are going to make some guest appearances to try to keep you paying attention. Moving forward, I'm going to start by taking umbrage with this year's Hotnet's call for paper. Specifically, this year's call for paper starts by saying, everybody loves TCP. And this isn't true because I don't love TCP, and I think that it's time for us to take TCP and throw it away. Specifically, I want to replace TCP, which is a stream transport protocol where all messages are treated the same, with MTP, a new message transport protocol where all messages are allowed to be treated differently. The rest of this talk, I'm going to start with some background. I'm going to move on to an overview of MTP and some evaluation. I'm going to start our background at a high level, and there are three main points I would like you to take away. First, TCP is old, outdated, and inflexible. Second, in-network computing is new and important because it's going to help us scale performance in a post-NARD area. And third, TCP is incompatible with in-network computing. The TCP standard is over 40 years old. Being 40 years old isn't inherently bad. There are lots of things that are 40 years old and have spawned lots of successful sequels. However, one problem with TCP being 40 years old is that it was designed before we knew a lot of things about computer networks. For example, TCP was designed 7 years before we even understood congestion control. However, the real problem that I have with TCP is that I've been trying to do something new recently, and TCP is getting in the way. Specifically, I recently acquired a Xilinx Alveo SmartNIC and a Barefoot Tofino switch. I've been trying to use these devices to accelerate distributed systems. What am I really trying to do with a SmartNIC and programmable switch? What I'm going to do is I'm going to take applications like Memcached and TensorFlow, and I'm going to run parts of them inside the network. And the reason that I want to do this is that CPU performance has plateaued. In some more detail, here's the type of system that I'm imagining. What we have is a cluster inside of our data center where each host might have a SmartNIC, and we're connected to programmable switches through some sort of complex topologies. Additional, more complex offloads might be implemented inside the network. In-network computing means two different things to me. First, it means implementing application-specific offloads inside the network, but there's another side to in-network computing to me. And this is the multi-path load balancing and resource part of it. The first thing, offloads, allows us to scale up performance, while the second thing, multi-path and multi-resource load balancing, allows us to scale out performance. Importantly, I think that both offloads and load balancing are needed to scale up performance in a post-NARD era. TCP is incompatible with in-network computing, and I'm now going to go over 5 reasons why this is the case. First, some offloads like compression and serialization need to mutate a message. Unfortunately, this is not possible with TCP stream abstraction, as sequence numbers will be wrong. Some of the devices in our network have limited processing capabilities with respect to the amount of packets they can buffer and how much computation they can perform. In short, we have potatoes in our network, and TCP is too complex to be processed by a potato. For fine-grained load balancing to work, it is necessary for different messages to be able to be routed to different back-end replicas. TCP cannot do this because different messages in the stream cannot be routed to different back-ends. At the same time, load balancing also breaks TCP congestion control. Like this example shows, when the client receives marked feedback from node 2, this is not usable because its next message is going to go to node 1 anyways. Performance isolation is also a key important property. In this case, we need to be able to ensure that our elephant flows are isolated from our mice flows. Fortunately, this is also not possible with TCP because it defaults to a per-flow fairness policy. In conclusion, TCP and in-network computing are incompatible, and it's time to move on and do something new. And this is exactly what I've done with MTP. I'm going to spend the rest of this talk going over the design of MTP. There are 2 main components to MTP. The first is a novel message-based transport protocol, and the second is a new pathlet congestion control protocol. Let's talk more about MTP's message transport. This transport protocol allows for messages to be mutated arbitrarily. Unfortunately, this causes problems with consistency. If you allow for messages to be arbitrarily mutated and arbitrarily load balanced across the network, this gets very difficult to be able to reassemble and use these messages correctly. TCP, all packets in the same message are treated the same, that they follow the same paths and are processed by the same devices. With applications that are generating short RPCs, each RPC is its own message, even if it contains multiple packets. However, this is not the case for applications that send bulk data through the network. File systems that are sending large chunks of data throughout the network have each packet marked as a separate message so that it can be processed differently and load balanced across the network. Next, MTP introduces a new approach to congestion control where the network is divided up into pathlets, and each pathlet has its own congestion control feedback and state. Exactly how to divide the network up into pathlets is left up to the operator in MTP. Each pathlet is then responsible for providing its own congestion control feedback, which can be an opaque type length value field. End hosts then evolve per pathlet congestion windows. To try to help make these two different components of MTP more clear, I'm now going to go through the MTP packet header format, version 1. First, the fields circled in blue here are used for routing and per message independence. Next, the fields circled in orange here are used for reliability, even in the face of messages that can change in data and size. Finally, the rest of the fields circled in green are used for the pathlet congestion control algorithm. First, we have a list that of paths that are excluded for use by the end host. The end host maintains congestion windows for every pathlet that it is aware of, and some of those may become congested. This path exclude count is used as a hint to the network to try to tell the network to not use a path that the end host thinks is already congested. Next, we have a path feedback list, and this is used to accumulate for every pathlet that a message goes through to add its type length value opaque congestion control feedback. Together, these enable both our message transport and pathlet congestion control. Next, this slide shows how the different components of MTP are layered together. At the top, we have applications that interface with MTP through the MTP application interface. Below this layer, we have the MTP transmission control layer. In this layer, every pathlet that the end host learns about has its own congestion control evolved. This allows for multi-algorithm congestion control. Each pathlet can have its own type of feedback and its own algorithm that involves its own window or rate. Below the transport layer, we have the MTP pathlet layer. This layer looks at the different rates and windows of all the pathlets and decides which paths to deselect and if and when to inject packets into the network. We envision two different types of offloads that can interact with MTP. The first is a limited capacity offload. In this model, the device performs only as much computation as needed to perform its offload and update the packet headers. Additionally, we also envision more fully functioned network offloads that can implement more complicated transport functionality. As we can see, by design, MTP is able to meet all of the requirements we have to be able to support in-network computing. Finally, I'm now going to talk to you about how we evaluated MTP. Our goal with our evaluation is to demonstrate that MTP can overcome the limitations of TCP and its variants like DC-TCP. To show that MTP can provide multipath congestion control, we consider the scenario of a hybrid optical electrical network. In this experiment, we have a fast optical connection that operates at 100 gigabit and a slow electrical connection that operates at 10 gigabit. The network switches between these paths every 1 millisecond in this experiment. This figure shows the results of this experiment. When the network switches between the slow 10 gigabit connection and the fast 100 gigabit connection, DC-TCP wastes bandwidth, ramping up its throughput over time. In contrast, MTP uses two congestion windows to ramp up throughput immediately when the network changes pathlet. Next, we consider a scenario where there are asymmetric path delays between the two different paths between a source and destination. We considered three different approaches to in-network load balancing. The first approach is ECMP. Although this avoids reordering, it also leads to uneven load in the network, which leads to increases in tail flow completion times. Next, we also considered packet spraying, which uses a per-packet round-robin algorithm to decide which path to use. Although this leads to good utilization, it also causes poor performance with TCP due to reordering. Finally, MTP in this experiment is able to achieve good load balancing without reordering. In our last experiment, we consider the scenario where there's asymmetric load. Given this asymmetric load, we then considered three different approaches to network isolation. First, we can see that DC-TCP and its per-flow fairness policy does not provide per-tenant isolation in this example. Next, we consider the scenario of virtual queues, which uses a resource inside the network to provide isolation. Although virtual queues provide good isolation, they are a scarce resource, so it is not always possible to do this for a large number of tenants. In contrast, MTP is able to perform per-traffic class congestion control feedback, and end hosts evolve per-pathlet congestion windows, and this allows for per-entity isolation without any dedicated resources inside the network. In conclusion, I've talked to you today about why TCP is harmful to in-network computing, and I've presented a new design of a message transport protocol that overcomes these limitations. Finally, MTP is a work in progress, so if you have any feedback or would like to talk to me more about this design, please feel free to reach out. I'd be happy to hear your feedback.